So we find that the first derivative and the first derivative test just verify what we already knew about that function. But here's something that calculus made a whole lot easier. Calculus also told us, because we are dealing with a parabola, the x-coordinate to the vertex of that parabola in the plane. Those are the kinds of things that help you when it comes to the ACT. Use calculus on the ACT. It's a multiple choice test. Nobody cares how you got to the right answer. They just care that you got to the right answer. Calculus can get us to the right answer a lot quicker sometimes than algebra can. Let's work another analytic example. Find the absolute maximum and minimum values of this function. This says that I should expect to find both a maximum and a minimum of this function. So let's take a minute, big picture, and look at our function. That is a cubic function. Here's what I know in general about cubic functions. They, depending on what's going on, they kind of look like that. I'm not expecting an absolute maximum or an absolute minimum on this function. The domain of this function is negative infinity to positive infinity. It's defined everywhere. Oh, but wait. I don't get to look over the entire domain of this function. I don't get to start looking until I reach x equal negative 1/2, and I have to stop looking at the graph of this function when I get to x equal 4. And these endpoints are included. I got all that information. All this is already floating through my head, and I haven't taken my derivative function yet. Take 5 or 10 seconds to orient yourself to what's going on with your function. If it's asking about global or absolute extreme values, take a minute to say, do I need to worry about endpoints of an interval? Do my critical points include endpoints? Make a plan. Don't just jump in head first. Make sure you understand why you're doing what you're doing, not just how you're doing what you're doing. So the process for finding critical points, that's the first step we're going to do. Number 1, critical points. And we would put specifically from the derivative, because there are other critical points we're going to pursue later. That looks like finding the first derivative function, which looks like that. Setting that first derivative function equal to 0, or determining where that first derivative function is undefined or does not exist. This is a smooth, continuous parabolic function. Not going to have any critical points that are candidates from the first derivative undefined. Don't forget what you know. What you know is that you don't solve this by saying 3x squared equals 6x. This is a quadratic function. You solve this by getting factors and by setting each factor equal to 0. So we have critical points, specifically stationary points, of x equals 0 and x equal 2. So let's run the first derivative test on those. Let's determine whether we're dealing with local maxes or local mins for these two critical points. I have two candidates. Just as we did for monotonicity, we're going to fill this out in the correct order. We're going to plug these values, these test points, into our first derivative function. We are looking for the sign, the SIGN of the first derivative at those test points. When I plug in to the first derivative function, I generally do it in that form. And I generally don't worry about value. I just worry about sign. That's all I'm after. When I plug -1 into this term, I get a negative value. When I plug -1 into this term, I get a negative value. A negative times a negative is a positive. When I plug 1 into the first term, I get a positive. When I plug 1 into the second term, I get a negative. A positive and a negative yields a negative for a product. This is multiply. When I plug 3 in, I get a positive out of the first term and a positive out of the second term. That product is going to be a positive value. I don't care what the value is. Many students have a really hard time not carrying the numbers with them. They want closure. I don't need to know what the value of the first derivative is at these test points. I need to know what the sign attached to that value is. That's all I'm worried about. So, I'm going to make myself some room here. And I have run the first derivative test. I don't have to identify it as the first derivative test, by the way. Any mathematician can clearly see that's what it is if you have labeled it correctly. Sometimes it helps. This was easier to do when you were in the room, when my students were in the room with me teaching. Hold your hand in front of your face. When you hold your hand up, you're going to hold it in such a way that it mimics a positively sloped line. Then this tells you that your slopes went to 0. So move your hand where it's flat in front of you. That is where your first derivative equals 0. Now move your hand with your fingers facing down, and that mimics a negative slope. And if you will do that very smoothly from positive to 0 to negative, you will see that you are in the air drawing yourself a maximum. Do the same thing for the other critical point. Start with negative slopes, fingers pointed down, then bring your hand horizontal, then put your fingers up in the air, and you have a min. So here the first derivative test says we have a max at x equals 0 and a min at x equal 2. The first derivative test has identified not only where we have extreme values, but what type of extreme values we have. So we're going to pick up those extreme values and we're going to evaluate our function at those two critical points, because it says find those extreme values of the function. I am using the derivative to identify where that might occur. But just knowing where that these extreme values might occur doesn't give me the extreme values themselves. So I'm going to go back to the original function and plug in these critical points. So that gives me 1, 2 cubed minus 3 times 2 squared plus 1 gives me 8 minus 12 plus 1 gives me negative 3. Am I done? Because I have a max at x equals 0 and a min at x equal 2, does that mean that I get to start using words down here that says the function f has a maximum of 1, an absolute maximum of 1, and an absolute minimum of -3. No. There are other candidates in this process that I have to determine and compare to these extreme values. If I find that f of -1/2 is a value bigger than 1, then f of -1/2 is the maximum. If I find that f of -1/2 is a value smaller than -3, then f of -1/2 is the minimum. I can have an extreme value at the endpoint of an interval. Here's one where the maximum happened at the left endpoint of the interval. For the visual learners, that's what we are exploring. You have to explore the output of the function at both endpoints. If you have a closed interval and the endpoints are included, they are candidates for where extreme values could happen. So -1/2 cubed minus 3 times -1/2 squared plus 1. Oh, help me. -1/8. This is minus 3/4 plus, I'm going to call that 8/8. I'm going to call this 6. You got to watch me. This is where I'm going to have issues. 6/8. So -7/8 plus 8/8 is 1/8, a positive 1/8. So this is smaller than an output of 1. Definitely not a candidate for the max. It is also larger than -3. Not going to be the min. But I had to check. Now let's put 4 into this function. Here we're going to get, I believe we get 64. 3 times 16 which is 48 plus 1. So 65 minus 48 is a positive 17. Here is the maximum. That just knocked 1 out of contention for the maximum value of the function on the closed interval. So I would answer this question, f of x has a global or an absolute max of 17 and an absolute min of -3. We have now answered this question. And that's, again, what your work should look like.